Greetings and welcome once again to my new calculus channel. I am John Gabriel, and today I'm going to present another short Pithy video on how to teach the operation of division. So let's begin. Now, you'll know from experience, because most of you are not good at mathematics, and it needn't be that way. There is no such thing as a human who cannot do mathematics, only a human who hasn't had a competent mathematics educator. So students never understand the operation properly because it is taught incorrectly by educators who themselves have never understood. So for example, Martha pays $10 for 5 ice cream cones. How much should she pay for each ice cream cone? So this problem is solved correctly by using simple measure. That is, we need to measure $10 with 5 ice cream cones by treating the 5 ice cream cones as a unit measure, that is $5. And you can see the scheme as I've illustrated in this slide here. We use line segments to indicate each dollar, and we simply use the $5 as a measuring unit. 1 and 2, right? So that's what we do there. Measure is 1 there. Right? Okay, and so that's really how we do all arithmetic. All our arithmetic comes to us from geometry and the way we perform the arithmetic using line segments and ratios of line segments. So reducing every problem to one where a simple measure is involved, such as taking a measuring unit and counting how many times the measuring unit fits into the given line segment or the magnitude, is the way we ought to do it. So this should be the starting point, but at a slightly more advanced age, students could learn a general method of division for any magnitude measuring unit, and this can only be done once they've learned geometry, for example, the geometry of similar triangles, etc. So now we can write this algebraic expression 10 over 5 in geometry as any of the following ratios that you see over here, because all of the above ratios are in proportion and their measure is the same. Their measure is 2, right? So we know how much to subtract from each of these ratios because from similar triangles, as you see in this slide here, we can simply move this line downwards and we can choose any of these ratios that we like. And of course, in algebra, we need to divide these into equal segments, but it doesn't matter in geometry, okay? And why do we need to do that in algebra? Because we need the measure of these ratios. And of course, this one here is the irreducible ratio. So as you can see, one could also perceive the same problem earlier as a ratio of dollars to cones. But in algebra, we ignore the actual units, the dollar and the cone, when finding an irreducible ratio, because algebra doesn't care about the actual unit. It only uses the abstract unit whose size is irrelevant, okay? So this problem can be changed so that we can say Martha pays $2 per ice cream cone, and if she has $10, how many cones can she buy? And again, it's the same story. In geometry, you might only arrive at a result of 5 if we attempt to measure the ratio, which could be any one of innumerably many such ratios. And as I've often told you, a number is the measure of a ratio, or a number is a name given to a measure that describes a magnitude. In particular, the magnitude I'm thinking about is the antecedent part of a ratio. So, since we cannot use similar triangles in algebra, it is required that in order for the geometric properties to function correctly, every measure must take place with fractions whose numerators and denominators are multiples of the abstract unit. Okay? Which means that in order for a denominator and or parts of a denominator to measure a numerator, it must theoretically be divided into equal parts. And this is also the reason you cannot divide by 0, because 0 is not a number, okay? And you can think about what I've written here by yourself. So I've gone a little longer than I wanted to. I tried to keep these to 3 minutes, But that's pretty much it. I'm John Gabriel, and this is the New Calculus channel. Till next time, goodbye.